You know how we all have that little corner of our brain that still thinks about space travel, not just like satellites and telescopes, but actually going to other
Oh,
worlds?
definitely, that sense of wonder.
Well, today on the deep dive, we're going to scratch that itch for you. We've pulled together a stack of really interesting stuff, research papers, news articles, even some pretty wild ideas about what's next. And we're going to give you the fast track to understanding when those sci-fi dreams of moon bases and Mars walks might actually become reality.
Exactly. Think of this as your personal briefing on humanity's next giant leaps. Our mission basically is simple, to give you a clear, engaging, and, dare I say, exciting overview of the concrete plans and the projected timelines for getting back to the moon and onward to Mars.
Yeah, what's actually happening.
Right. We'll also touch on the monumental challenges involved and maybe even peek at some of the more distant, almost unbelievable possibilities.
All right, let's dive in, shall we? First up, our nearest celestial neighbor, the moon, and NASA's Artemis program. Now, this isn't just about planting a flag and coming home, right? This feels different from Apollo.
Precisely. What's key to understand about Artemis is the shift in mindset. Apollo was about those incredible short sprints to the surface. Artemis is a marathon focused on building a sustained
A
presence.
marathon, okay.
Think of it this way. Apollo was like a series of impressive expeditions. Artemis is about setting up a permanent research outpost and learning how to live and work off-world long-term. The strategic implications for things like, resource utilization and scientific discovery are huge.
Right. It's been over half a century since we last had astronauts on the moon, and Artemis is aiming to change that in a big way. We had the successful uncrewed Artemis test flight in late 2022, a crucial shakedown cruise for the hardware.
Very important test. Yeah.
And next up, targeted for late 2025, is Artemis II. This mission will send astronauts on a flyby around the moon. What's the big deal about just a flyby? Seems kind of like a near miss.
Well, that flyby is actually a critical step. It's the first time we'll be putting humans back in that deep space environment in the Orion spacecraft.
Okay.
It allows us to rigorously test all the life support systems, the navigation, everything with a crew on board before we even attempt a landing. It's about identifying and mitigating risks in the proving ground of lunar orbit.
Makes sense. Testing the waters, basically.
Exactly.
And then comes Artemis III, the one with the really ambitious goal of landing the first woman and the first person of color near a moon's south pole. That's currently slated for 2026, which feels surprisingly close.
It does feel close, yeah.
Why the South Pole, though? It's not exactly where the Apollo missions went.
The South Pole is the new prime real estate on the moon, and it all comes down to water ice.
Water ice, right.
For billions of years, shadowed craters in that region haven't seen sunlight, and as a result, they become natural freezers, trapping significant amounts of water ice.
Mm.
And this ice, as you can imagine, is incredibly valuable.
More valuable than gold up there, probably, because it's not just for drinking, is it? You can break it down.
Exactly. Electrolysis can split that water into hydrogen and oxygen, the fundamental ingredients for rocket propellant. So imagine being able to refuel spacecraft on the moon.
Wow. Game changer.
Huge game changer. Plus, you get breathable air and, of course, water for sustaining a lunar base. This resource completely changes the long-term viability of lunar settlements.
So this go to the moon and stay there idea that NASA talks about, it's really predicated on accessing these resources. And to make that happen, there's a whole infrastructure being planned, right? Not just landing and leaving.
Absolutely. Think of it as building a small outpost in a remote location. You need a central hub. That's where Gateway comes in.
Wait, okay.
It's a planned small space station orbiting the moon, acting as a transfer point for landers and a platform for research. Then, on the surface, the vision is a habitable base camp, allowing astronauts to conduct longer duration missions, weeks or even months at a time.
Weeks or months, that's a big difference from Apollo's few days.
Huge difference.
And the moon isn't just the end goal here, is it? It's seen as this crucial stepping stone on the way to the ultimate prize, Mars.
Precisely. The moon offers a relatively close-by environment to test out the technologies and procedures we'll need for those much longer and more complex deep space missions to Mars.
Practice makes perfect, even in space.
As NASA Administrator Bill Nelson has said, Artemis is showing what we can achieve when we work together on ambitious goals. It's our training ground for living and working beyond Earth's immediate vicinity.
we're talking about developing and testing some pretty sophisticated hardware, from the powerful SLS rocket and the Orion crew capsule to the specialized lunar landers and the next generation spacesuits that will allow astronauts to really explore the lunar surface.
And it's a fascinating blend of government and private enterprise driving this forward. SpaceX, for example, is developing a version of their Starship spacecraft to be the lunar lander for Artemis III.
Right, Starship. That's a big part of this.
This kind of commercial involvement is quite different from the Apollo era and brings a different dynamic to innovation in space travel. The overarching goal, really, is to transform the moon from a place we visit to a place where we can truly live and work, leveraging its resources and expanding humanity's footprint in the solar system.
Okay, so the moon is the first major leap. But let's be real, the red planet has always captured our collective imagination. So let's shift gears and look at the plans for reaching Mars. It feels like we've been hearing about this forever.
It has been a long-held ambition, hasn't it? And while our robotic explorers like Perseverance and Curiosity continue to send back incredible data and images from the Martian surface.
Doing amazing work, those rovers.
Absolutely.
Hmm.
But the drive to send humans there remains a powerful one. It's the next logical horizon.
And NASA's current official target is to land astronauts on Mars around 2040. That sounds like a long way off, but in the grand scheme of things, it's within the lifetime of many of us.
It is, yeah.
The envisioned mission is pretty intense, right? Months just to get there, about a month on the surface, and then a long haul back.
That roughly 2 to 3 year round trip really highlights the immense scale of this undertaking. NASA leadership has openly acknowledged that landing humans on Mars by 2040 is an audacious goal, but they are actively investing in the technologies and research needed to make it a reality.
And we're already seeing some really clever technologies being tested. Take OMSI, that little gadget on the Perseverance rover.
Oh, yes, MAC.
It actually managed to create oxygen from the Martian atmosphere, which is almost entirely carbon dioxide. That's like science fiction becoming reality.
What's truly insightful about OMSI isn't just that it worked, but what it implies for the future. While it was small, think toaster-sized, it proved the fundamental concept.
Proof of concept, right?
Imagine scaled-up systems that could produce the vast amounts of oxygen needed, not only for a crew to breathe, but also as a key component of rocket propellant for the journey home. It's about learning to live off the land, utilizing the resources Mars has, however meager they may seem initially.
Exactly. Just like the water ice on the moon. It's ISRU, in situ resource utilization.
That's the term, yes.
And it's not just about breathing air. They're also working on next-generation spacesuits specifically designed for the Martian environment, figuring out what kind of habitats we'd need, and even experimenting with growing food. I think I remember reading about trials with potatoes, which has a certain Martian movie charm to it.
Right down to the Matt Damon references, absolutely. But the challenges of that long interplanetary journey are significant. We're talking about a launch window to Mars that only opens up roughly every 26 months when Earth and Mars are in favorable orbital positions.
Only every couple years.
Right. And even then, the one-way trip can take anywhere from 7 to 10 months. Can you imagine spending that much time in a relatively confined spacecraft with the same crew?
Cabin fever on a cosmic scale. And once you arrive, you're incredibly far from Earth. Forget about a quick call home. There can be significant communication delays, several minutes each way.
That's right, up to 20 minutes one way, depending on orbital positions.
It really underscores the need for these missions to be almost entirely self-sufficient.
Precisely. Reliability and redundancy will be paramount. If a critical system fails, the crew can't just wait for a resupply mission from Earth. They'll need to be able to diagnose and fix problems themselves, grow their own food, recycle their water and air. It demands a whole new level of mission planning and crew training.
Now, while NASA has that 2040-ish time frame, we also have Elon Musk and SpaceX with a much more, let's say, accelerated vision for getting to Mars.
Accelerated is a good way to put it. Musk's ambition isn't just about a brief expedition. It's about establishing a permanent, self-sustaining colony on Mars.
A colony, not just a visit.
Right. He's talked about potentially sending uncrewed Starship test flights to Mars as early as 2026, with the first crewed missions potentially following around 2028.
And we've seen those Starship orbital test flights happening in 2024 with that really rapid development and testing cycle that SpaceX is known for blowing things up and learning from it, basically.
Iterate, iterate, iterate. That's their mantra.
Musk's ultimate goal of a million-person city on Mars by the mid-21st century sounds almost fantastical.
It's certainly an incredibly optimistic long-term vision, and Many experts have varying degrees of skepticism about those specific timelines.
Understandably so.
However, the fact that you have both government agencies and private companies with serious, well-funded efforts underway to reach Mars is a historically significant development. It signifies a real momentum.
Yeah, it's not just one entity anymore. And let's not overlook China's ambitions in space. They've also laid out some pretty significant Mars plans,
They have indeed.
aiming for a crewed mission in 2033 and looking towards establishing a long-term base with regular flights in the decades that follow. They're even planning robotic missions to scout out resources beforehand, which seems like a very methodical approach.
Very strategic. This really does feel like a new kind of space race in the 21st century, although perhaps one with more potential for international collaboration than the Cold War era. The U.S., through NASA and its commercial partners, and China are both pushing the boundaries of what's possible in deep space travel.
So if we piece it all together, the next couple of decades could be pretty amazing. We're looking at potential human return to the moon in the mid-2020s, a more established lunar presence by the 2030s, and then those first human footprints on Mars sometime in the late 2030s or 2040s. It's a truly exciting roadmap.
It is, but it's crucial for you to understand that sending humans beyond Earth's protective embrace is an extraordinarily difficult endeavor. Space, while inspiring, is an inherently hostile environment.
Right, not exactly welcoming.
For all these ambitious plans to become reality, we have to overcome some fundamental and very significant hurdles.
Okay, let's talk about those hurdles. And the first one that always sounds the most menacing is space radiation. It's not like getting a sunburn, is it?
Not even close. Once astronauts venture outside Earth's magnetic field and atmosphere, they're exposed to a constant barrage of high-energy radiation from the sun and from deep space, things like galactic cosmic rays.
GCRs, yeah.
These are incredibly energetic particles that can penetrate spacecraft and even human tissue, potentially causing damage to cells and DNA.
I remember reading a really vivid description that compared it to tiny bullets constantly flying through your body, potentially disrupting cellular function. That sounds pretty scary over a long-duration mission.
It is a significant concern. Over the course of a multi-year mission to Mars, this cumulative exposure can substantially increase the risk of cancer and potentially cause damage to the nervous system.
Your nervous system, too. Wow.
And then you have unpredictable solar flares, which can deliver sudden, intense bursts of radiation that could be acutely life-threatening.
So cosmic rays are the constant drizzle. Solar flares are the sudden downpours.
That's a good analogy. And the natural shielding we have here on Earth, we just don't have that same level of protection once we leave our planet, right?
Nope. No magnetosphere, no thick atmosphere out there.
Exactly. And designing effective shielding for spacecraft is a really complex engineering challenge. Heavier shielding offers more protection, but adds significant weight, which dramatically increases the cost and difficulty of launching.
The eternal tyranny of the rocket equation.
Precisely. Some of the solutions being explored include incorporating materials like water or polyethylene into the spacecraft's structure to absorb radiation, or even the idea of building habitats on the Moon or Mars that are either underground or covered with a thick layer of regolith lunar or Martian soil for natural shielding.
Burying the habitats, basically.
Essentially, yeah. Using the planet itself as a shield.
I've also heard about research into pharmaceuticals that might help protect the body from radiation damage or enhance its ability to repair itself. It sounds like a multi-pronged approach is needed.
Absolutely. As many experts in the field emphasize, effectively mitigating the risks of space radiation is going to be a critical factor in determining the feasibility and safety of long-duration human missions to Mars and beyond. It's arguably the primary physiological challenge.
All right, another major issue is gravity, or the lack thereof, or the different levels of gravity we'd encounter on other worlds. Our bodies are designed for Earth's 1G.
Precisely. Our physiology has evolved to function optimally under Earth's gravity, and we see significant negative effects when that's altered. On the International Space Station, in microgravity, astronauts experience muscle atrophy, their muscles weaken, and a significant loss of bone density, almost like a rapid acceleration of osteoporosis.
It's sobering to think that astronauts can lose bone density in space at a rate many times faster than someone with osteoporosis on Earth, like 1–2% per month.
It is quite dramatic, yeah, in that ballpark. And while some of that bone density can be regained upon returning to Earth, it's not always a complete recovery. And the longer the duration of the mission, the greater the risk of permanent skeletal damage.
So permanent damage is a real risk.
It is. Astronauts on the ISS have rigorous daily exercise regimes, treadmills, resistive exercise machines to try and counteract these effects. But it doesn't entirely eliminate the problem.
And a trip to Mars presents even more complexities. We're talking about a 6 to 9 month journey in near zero gravity each way, followed by time on Mars, which has only about 38% of Earth's gravity. We don't even know for sure if that level of gravity is sufficient to maintain long-term human health.
That's a fundamental unanswered question. Is Mars gravity enough? We just don't know. There are also other physiological issues associated with prolonged exposure to microgravity, such as fluid shifts within the body.
Yeah, the puffy face thing.
Right. And the psychological impact of being weightless for such an extended period. Scientists are investigating potential countermeasures, from specialized medications to combat bone loss to advanced exercise protocols, and even the potential for artificial gravity systems, perhaps rotating sections of a spacecraft.
Artificial gravity? Like in the movies?
It's a serious engineering challenge, but it's being looked at.
It makes you wonder about the physical condition astronauts will be in when they finally arrive on Mars after that long transit. Will they even be strong enough to perform the tasks required of them?
That's a very valid concern. Imagine arriving on an alien world and struggling with basic mobility. While the lower gravity on the Moon and Mars will make lifting heavy objects easier, the long-term effects of reduced gravity on overall health and physical capability are a major focus of ongoing research. Still need strong bones and muscles.
Okay, so we've got the invisible threats of radiation and the constant pull or lack thereof of gravity. What about the really basic stuff? Keeping people alive with air, water, and food in the harsh environment of space.
Ugh. Life support. Yes, an incredibly intricate engineering challenge. Here on Earth, we take these essentials for granted. In space, everything has to be meticulously managed, conserved, and often recycled.
Nothing wasted.
For breathable air, primarily oxygen, the ISS uses electrolysis to split water molecules. For Mars, the MOXI experiment was a significant proof of concept, demonstrating the ability to extract oxygen from the carbon dioxide-rich atmosphere. Future Mars missions will almost certainly need to produce their own oxygen and water on a much larger scale.
And water is incredibly heavy to launch, so efficient recycling has to be a top priority, doesn't it? I remember that slightly unappetizing but very practical phrase, yesterday's coffee is tomorrow's coffee.
That's the unvarnished truth of life support in space. Astronauts on the ISS already recycle a very high percentage of their water.
Like 98% or something crazy.
It's getting up there, yeah. On the Moon and Mars, the potential for extracting water ice directly from the regolith offers another potential source, linking back to Artemis and the South Pole.
It all ties together.
Food is another critical factor. You simply can't pack enough prepackaged meals for a multi-year mission. Growing food in space is going to be essential for long-duration stays and any permanent settlements.
We've seen those small-scale experiments on the ISS with growing leafy greens. The idea of having dedicated greenhouse modules on future spacecraft, or even establishing controlled agriculture on Mars, is pretty mind-boggling, but seems increasingly necessary.
And then you have the habitats themselves. They need to maintain a stable and habitable internal environment, temperature, pressure, air composition, in the face of extreme external conditions, like the frigid temperatures and thin atmosphere of Mars.
Big temperature swings on Mars, too.
Huge swings. Powering all these life support systems, along with scientific equipment and communication, will likely require robust and reliable power sources, potentially nuclear reactors or large solar arrays coupled with advanced battery storage.
Nuclear power seems almost inevitable for Mars base, doesn't it?
For reliable, continuous power, especially through dust storms or long Martian nights, it's a very strong contender. And we shouldn't forget the crucial aspect of the crew's psychological well-being during those long periods of isolation, far from home.
Yeah, the mental health aspect is huge.
It really sounds like the ultimate goal is to create a miniature, self-sustaining Earth ecosystem wherever we venture in space.
A little bubble of Earth.
Precisely. And then, of course, there's the elephant in the room, the sheer cost of sending humans to other planets. It's an endeavor with a massive price tag.
We're talking billions of dollars just for the Artemis program, and each launch of that massive SLS rocket is incredibly expensive. It makes you wonder about the long-term economic sustainability of these ambitions.
Historically, a significant portion of the high cost of spaceflight has been due to the expendable nature of rockets. We essentially threw them away after a single use. It's akin to building a brand new airplane for every single flight.
Wild when you think about it that way.
However, the paradigm shift we're witnessing now is the advent of reusable rocket technology, pioneered most notably by companies like SpaceX.
Those Falcon 9 boosters that can land themselves and be flown again have already brought launch costs down significantly. And now SpaceX is aiming for full reusability with their Starship,
The holy grail of rocketry.
which has the potential to reduce the cost of reaching orbit to just the price of the fuel. That would be a game changer for Mars missions, wouldn't it?
Absolutely. If Starship can achieve those dramatically lower launch costs, it would make transporting the massive amounts of cargo and the large crews needed for establishing a Mars colony far more economically feasible.
Makes the whole colony idea seem slightly less fantastical, maybe.
It certainly helps the economics. Beyond reusable rockets, there's also exciting work being done on alternative propulsion technologies, such as nuclear thermal rocket engines. NASA and DARPA are collaborating on the Duraco program, aiming for a flight demonstration as early as 2027.
Nuclear thermal rockets, that sounds like something out of the Cold War era. How do they work, and what's the advantage?
Well, instead of chemical combustion, a nuclear thermal rocket uses a nuclear reactor to heat a propellant, typically liquid hydrogen, to extremely high temperatures. This superheated propellant is then expelled through a nozzle to generate thrust.
So much hotter exhaust, more efficient push.
Essentially, yes. The key advantage is significantly higher efficiency compared to chemical rockets, meaning you get more thrust for the same amount of propellant, which translates to faster travel times in deep space.
Mm.
This could dramatically shorten the journey to Mars,
Cutting down that 7-10 month trip.
reducing the crew's exposure to radiation and the logistical challenges of a long-duration mission. There are also more futuristic propulsion concepts being explored, like ion drives, solar sails, and even fusion rockets, but these are still largely in the research and development phases.
Ion drives are great for efficiency, but low thrust, right? Solar sails, fusion, way down the line.
Pretty much. And of course, it's not just the spacecraft itself. You need all the supporting infrastructure communication networks, robotic landers for scouting, habitats on the surface,
Right.
and all of that adds to the overall cost.
It's a whole system, not just one rocket.
It is. However, the potential for international collaboration in these ambitious endeavors is much greater now than it was during the Apollo era. Sharing the financial burden and pooling expertise could be a crucial factor in making these long-term goals achievable.
Makes sense. Spread the costs, spread the knowledge.
And there's also the growing hope that as space technology matures and we learn to utilize resources we find in space, that ISRU concept, again, the economic equation will begin to shift. We've seen how technology has driven down costs in other industries, and there's reason to believe the same will happen with space travel in the long run.
It's a formidable list of challenges: radiation, gravity, life support, cost, propulsion. But as you pointed out, none of them seem fundamentally insurmountable with enough ingenuity and persistent effort. It's that human drive to explore the unknown, isn't it?
Precisely. Think back to the early days of aviation. Crossing the Atlantic seemed like an impossible feat, yet within a few decades it became commonplace. The obstacles to reaching Mars and other worlds are significant, but with sustained investment in research and development, and with the kind of innovation we're currently seeing, those seemingly insurmountable challenges can likely be overcome.
Okay, so we've explored the near-term goals of returning to the moon and the more ambitious plans for Mars. But let's indulge in a little bit of far-out thinking. What about venturing even further to Jupiter's moons, Saturn's Titan, maybe even someday exoplanets around other stars?
Now we're really dreaming big. This is where we move into the realm of longer-term speculation, but it's important for setting our ultimate horizons and inspiring the research of today.
Keeps us looking up.
We haven't yet sent humans beyond the moon, but the potential of exploring these more distant worlds holds immense scientific and philosophical appeal. Jupiter's moons, for instance, are incredibly diverse and intriguing. Europa, with its subsurface ocean, which could potentially harbor life.
The big one for astrobiology.
Ganymede, the largest moon in the solar system and the only one with its own magnetic field. And Callisto, which lies outside Jupiter's intense radiation belts.
Callisto sounds like maybe the safer bet for a base.
Potentially. I recall reading about a conceptual study from NASA in the early 2000s, Project Hope, that looked at the possibility of a crewed base on Callisto sometime in the 2040s, powered by nuclear propulsion. That sounds like deep science fiction.
2040s for Jupiter. Wow, that was ambitious even then.
It does have a very forward-looking feel, and it was indeed a conceptual study, highlighting the potential but also the immense challenges. Getting to Jupiter takes years, 5 or 6 years one way.
Years!
And the radiation environment around some of its moons is extreme, necessitating very robust shielding.
So if a trip to Mars is a long camping trip, what kind of epic journey would a mission to Jupiter be?
It would be more akin to a multi-year ocean voyage to a distant continent after a very, very long camping trip. It would likely involve assembling massive spacecraft in Earth orbit, potentially incorporating artificial gravity for the years-long transit, and possibly even establishing robotic precursor missions and in-space refueling depots. A massive undertaking.
But imagine the discoveries. Landing on a moon like Callisto and then using remotely operated robots to explore the hidden oceans of Europa, or maybe even sending probes into the atmosphere of a gas giant like Jupiter itself. That's mind-boggling.
The science return would be phenomenal. And then there's Saturn's moon Titan, a truly unique world in our solar system, with its hazy atmosphere and lakes of liquid methane.
Methane lakes. So weird.
Remarkably, the atmospheric pressure on Titan is actually similar to Earth's, so theoretically, a human could walk on the surface with just an oxygen mask and protection from the extreme cold.
Just need a warm coat and an oxygen tank.
Basically, yes. The warm is relative. It's incredibly cold. Plus, with its low gravity and dense atmosphere, the idea of human-powered flight with wings becomes a tantalizing possibility.
Wow, flying on another world with wings. That's an image that will stick with me, but I'm guessing a human expedition to Titan is still a very distant prospect.
Likely centuries away, unless we see some truly revolutionary breakthroughs in propulsion technology. And then, of course, we have the realm of exoplanets, the thousands of planets we've discovered orbiting stars beyond our sun,
Thousands now, it's incredible.
including many that are Earth-sized and located within their stars' habitable zones. The idea of one day visiting another Earth-like planet is profoundly exciting.
But even the closest known exoplanet, Proxima b, is over 4 light years away. That distance is almost impossible for our minds to grasp.
It's an absolutely staggering distance, trillions upon trillions of miles. With our current propulsion systems, even chemical or nuclear thermal, a journey to even the nearest star system would take tens of thousands of years.
Tens of thousands.
To put it in perspective, the Voyager 1 spacecraft, one of the fastest objects we've ever launched, would take over 73,000 years to reach Proxima Centauri.
So interstellar travel, as depicted in science fiction warp drives and jumping through hyperspace that's firmly in the realm of fantasy for now, we'd need some fundamental shifts in our understanding of physics.
Precisely. We need physics we don't even know exists yet, probably.
Yeah.
There are some very early-stage research efforts, like the Breakthrough Starshot project.
The little nano probes with lasers.
Right, which aims to send tiny laser-propelled probes to nearby stars. But even those are uncrewed and would take decades to reach their targets. For human interstellar travel, concepts like multi-generational starships or some form of suspended animation are purely theoretical at this point.
Generation ships. Suspended animation. Pure sci-fi.
So, while the idea of reaching exoplanets is incredibly inspiring, it's definitely not on the near-term roadmap for any space agency.
Not in any practical sense, no.
Not in any practical sense. It remains a long-term aspiration that fuels fundamental research. However, it's crucial to remember the historical trajectory of technological progress. Things that once seemed utterly impossible can become reality with time and persistent scientific inquiry.
Like going from the first airplane flight to landing on the moon in just over half a century, you can't really predict what breakthroughs might occur.
Exactly. Our understanding of the universe and the laws of physics is constantly evolving, and future discoveries could open up possibilities we can't even imagine today. Scientists are actively exploring concepts like the Alcubierre warp, drive a theoretical way to distort space-time, and conducting small-scale experiments aimed at manipulating space.
Still very theoretical, but people are thinking about it.
So, while interstellar travel remains a distant dream, it serves as a powerful motivator for pushing the boundaries of what we know and what we can do.
So it seems the likely path forward is a step-by-step progression. First, establishing a sustainable presence in Earth orbit, then a return to the moon, and building a long-term infrastructure there, followed by the monumental undertaking of reaching Mars. And then, perhaps, much further down the line, venturing into the outer solar system, maybe the asteroid belt or Jupiter. Each step presents its own unique and significant challenges.
Precisely. But with each step, we gain invaluable experience, develop crucial technologies, and expand our understanding of what it takes for humanity to thrive beyond our home planet. Each one builds on the last.
Well, this has been an absolutely fascinating deep dive into humanity's near and not so near future in space. It really feels like we're standing on the cusp of some truly incredible achievements.
It does. We are living in a new era of space exploration, with significant advancements in human-rated spacecraft and a renewed global focus on venturing beyond Earth orbit. The prospect of returning to the moon in the coming years, with Artemis and establishing a permanent foothold there, feels increasingly within reach.
Yeah, the moon base seems almost tangible now.
And Mars, while a much more ambitious undertaking, is no longer just a far-off dream. There are active plans, dedicated research efforts, and even potential timelines that could see humans walking on the red planet within the next couple of decades. It's a truly exciting prospect for generations alive today.
Imagine seeing that happen.
And while there will undoubtedly be obstacles and potential delays along the way, space is hard, right?
Yeah.
The fundamental human desire to explore, to push the boundaries of what's possible, is a powerful driving force.
Absolutely.
We're also seeing rapid advancements in crucial technologies, from radiation shielding and closed-loop life support systems to space-based agriculture and even 3D printing for off-world construction, that are making the idea of living and working on other worlds increasingly feasible.
All these supporting technologies are maturing.
It paints a really compelling vision of the future. A future where humanity is not confined to a single planet, perhaps with lunar outposts, and even the very beginnings of a small Martian settlement by the end of this century.
A multi-world species.
And it all builds upon the foundational work that is happening right now. The Artemis missions to the moon are directly informing our strategies and developing the technologies we will need for the much more challenging journey to Mars. Each step we take, no matter how incremental it may seem, is paving the way for those future giant leaps.
So as you go about your day, consider this. The likelihood of humans not just visiting but actually living on other planets and moons is higher now than it has ever been in history, as long as we maintain the will and the commitment to keep pushing forward.
It's a choice we make, really.
Keep an eye on the progress, because you just might witness the dawn of humanity becoming a multi-world species firsthand. Thanks for taking this deep dive with us.